Well, as Anna said, I'm Clarisse. I'm from the University of Queensland. And before starting, I would like to acknowledge that I'm on the stolen land of the Turrbal people here in Brisbane and pay my respects to their elders past, present, and emerging. So today I'm going to talk to you about the life cycle of the fluke, platyhelminth trematode parasite of the family Demozoidae. Trematodes are internal parasitic flatworms whose diversity is highest in fishes, especially in marine fishes. They have very complex life cycles involving invertebrate and vertebrate hosts. And if you look at the small diagram here, that's typically what they look like. It's an elongated shape with annual sucker and a ventral sucker. Within the Trematoda, the superfamily Hemiroidea is found in terrestrial, freshwater, and also marine environment. Blessedly, the superfamily is monophyletic. It's composed of 16 families and comprises about 1,000 species. So it's one of the biggest groups of all the Trematoda. They are highly diverse morphologically, these families, so much so that if we look at them, the adults don't have any morphological common trait that binds all the families. That's just too diverse. So the only thing they have in common will be concerning the life cycle. The life cycle of a hemorrhoid is very much like life cycles of many other trematodes. It starts with an adult in a definitive host, here a fish. That adult will shed eggs into the environment. The eggs will hatch into the Marasidium larva, which can swim, and it's going to infect the first intermediate host. That intermediate host can be a bivalve, a scalpel mollusk, or a snail in the case of hemorrhoids. And most often it's going to be a snail. And that's very important because trematodes are understood to be very highly specific in terms of their first intermediate hosts. And so any change in that host at the family or even subfamily level is quite significant. In there, the Metacidium is going to transform into a mother radiata, which will in turn give birth to many daughter radiae. So there is an amplification of the number of parasites from one to many. And an amplification will keep going on as each daughter radiata will in turn give birth to thousands of cystophorus cercariae. Now, the cystophorus cercaria is what makes hemorrhoids hemorrhoids. As far as we know, they all have that. So if you look at it, it has a small cercarial chamber here, and normally the cercarial body is contained in that chamber. But when, upon emerging from the first intermediate host, the cercaria gets eaten by the second intermediate host, a delivery tube is unfolded and the cercarial body is forcibly injected into the gut wall of the second intermediate host, which is a very efficient way to ensure that the second intermediate host is going to be infected directly in its tissues. So the cercariae will be eaten by either copepods and or small fishes and then trophically transmitted to progressively bigger and bigger animals. In the process, they will become metacercariae, and eventually, hopefully for them, they will be trophically transmitted to the definitive host, thereby closing the life cycle. Today, I'm going to talk to you about specifically the family Didymozoidae. These species of this family are tissue dwellers, specialized tissue dwellers. They are found in marine or freshwater environments. They often come in pairs. You need to imagine a cyst and these two little things bundled together and looking at you funny. They have no eyes, but that's fine. So they often come like that. The family is composed of 6 subfamilies, many tribes, and about 250 species. So it's one of the biggest families of the Trematoda. And they come in absolutely crazy morphologies. They look nothing like other trematodes. We have pumpkin, we have little boats, we have bananas, whatever. They just don't look like any trematode at all. Also, it's assumed that they have 3 to 4 host life cycles, but the truth is we, until recently, didn't know, because until recently, no didymozoid life cycle was known at all, and especially the identity of the first intermediate host was a complete mystery. Now, the subfamilies, the systematics of the subfamilies is morphology based, unfortunately, and the first criterion is to know whether the bodies of the specimens are divided, like on the right, into an anterior extremity that is small and a big bulgy posterior extremity, or more thread-like, like on the right. The second criterion is to see whether the specimens are hermaphroditic or gonochoristic, which has nothing to do with the body shape. And the third is to see whether the individuals paired together have fused their tissues or if they are separable. If you see on the left, these are two individuals. You can see the heads here and here, but their posterior extremities have completely fused together. So they will have 2 pairs of testes here, another 2 pairs of testes, and then their ovary, they're everything, but they will be inseparable. Whereas on this side, for example, you will more have a big female and a very small male sitting in a cavity somewhere here, protected by the female body. If we go down to the tribes, then it becomes even more complicated because then we have to deal with either the presence or absence of the ventral sucker and the number and shape of the different organs, which can be tubular or completely branched and going everywhere, like on this drawing, for example. You have here an ovary that is doing, I don't know what, probably branched, and a vitellarium, meaning the organ that makes the egg shell, also probably branched and looping around. My first result is that a cystophorus cercaria, so a hemorrhoid cercaria, was found in this bivalve in Moreton Bay in Queensland. And after proper molecular analysis, we found a perfect match in ITS-228S rDNA with a didymozoid adult dwelling in the fin membranes of this fish, Elaps hawaiiensis, in the same area. We also found a perfect match in ITS2 with metacercarial larvae, so didymozoid larvae, from whiting. And this is a very extraordinary discovery because it allows us to present the first, at least partial, if not complete, didymozoid life cycle with the most important hosts, the first immediate host and the definitive host here. And the fact that these didymozoid species uses a bivalve has deep implications regarding didymozoid evolution as a whole. The first question to be asked is whether all bivalve infections belong to didymozoids. Well, only 6 families out of 16 have known life cycles. And out of these, only three of these 6 use snails. Of the ones that don't, only the didymozoidae are found in bivalves so far with my study. And in addition, only 4 of the 55 unassigned anonymous cystophorus infections ever recorded are not from snails. So bivalve infections in hemorrhoids are a rarity, really. And given this data, we can think that probably all the bivalve infections are going to be didymozoid in nature. The second question to ask is whether all didymozoids use bivalves, and this one is trickier. We know that above 26 species of bivalves are used by trematodes as first immediate hosts. However, only a maximum of 2 bivalve families have hemorrhoids and didymozoids in them. And this is very low compared to, for example, a non-hemorrhoid family like the Bucephalidae, another trematode family that is found only in bivalves, but they use 20 families of them. So whereas we have only 2 for hemorrhoids, therefore we think that what happened was a host shift within the didymozoids, where one branch of them took to start using bivalves, evolving them whereas maybe the bulk of the didymosoids is still to be found in snails. Obviously, we can't prove that because we haven't explored all the populations of all the bivalves in all the world, but that looks to us quite a parsimonious explanation. My second result is that the adult from Elops hawaiiensis in Moreton Bay have unique combination of morphological features that don't fit in any existing genus. So we decided to raise them as new genus and species. We named it Sacchalarina magnestabula, that new species. And it looks like that. These are my drawings. So it's a tape form. But now the difficulty was to know where to fit that genus, in which subfamily. So we turned to the molecular tool. And we built a 28S rDNA Bayesian inference tree of all the hemiuridia. And we got 5 of the 6 didymosoid subfamilies in there, which is really good. And we found out that the Sacchalarina magnestabula and 2 other uncharacterized taxa form a clade that is actually sister to all the other didymosoids we collected. So we thought, oh, maybe we should raise this to new subfamily then. Except no, because all the subfamilies within the Didymosoidae are polyphyletic. These are the 2 most specious subfamilies of the Didymosoidae, so Didymosoinae and Hematobothrinae. They go all over the place. And what is worse, the genera are also paraphyletic and polyphyletic. So it's a bit of a complete mess. Same for these ones. We found out in ITS2, where I had more genera to play with, that they are also polyphyletic and paraphyletic, although they don't look like it in the 28S data. This subfamily, the Didymodeclininae, is actually the only one for which I have a bit of hope left. Unfortunately, I am missing 1 genus out of 2, so I can't be sure either. So then, what to do with Sacchalarina? Well, we decided to raise it as a genus Incertacedes to the Didymosoidae because a complete overhaul of the didymosoid systematics and classification is an absolutely daunting work. These are extremely hard parasites to work with, and it would take an immense amount of effort in collecting and processing to be able to maybe sort something out molecularly and morphologically. So we are happy calling it an Incertacedes. And that's it for me. Thank you very much.
Fantastic. Thank you, Clarisse. We've probably got time for one really quick question. If somebody's got one, there's nothing in the chat. And I've just got one really quick question because I know nothing about marine life and even less about marine parasites. How long is their life cycle?
How long in terms of time, you mean?
Yeah.
Well, some parasites, trematodes in general, are very good at waiting until their host gets eaten by something. Provided they don't die of old age, they can wait pretty much all the time. So it really depends. Yeah, it depends on the concentration of hosts and prey and how efficient the life cycle can be completed in a particular area.
Cool, thank you.